Hello everybody. I hope you all are okay and safe wherever you are. Um, so as you all already know, class will resume online starting from Monday. So I have been working on the transition from in-class lecture to online lecture. So I set up this, what you see, kind of classroom at my home in my garage. Before I record the formal lecture and upload the video on D12 or on my website, whichever works, I just want to prepare a few minutes video clip and upload it and get back your feedback. So I just want to make sure what I write on the board and what I'm going to show you here on the screen, okay, is visible to you, is clearly visible to you. Okay, so just as a trial lecture, so I'm going to talk about the electromagnetic waves in a vacuum. Last time, I believe we derived the wave equation, so that's what I'm going to do as a trial lecture. So if you recall, we started from Maxwell's equation. So these are the Maxwell's equation, which includes the divergence of the electric field is equals to rho, the charge density, over epsilon naught. And the second one is the divergence of the magnetic field equals to what? 0. And the third one is the curl of the electric field, which is equals to minus the time change of the magnetic field. And the last one is the curl of the magnetic field, minus 1 over c squared d E by dt is equal to mu naught times the charge density. So these are the Maxwell equations from which we started to determine the wave equation for electromagnetic waves. So I will stop here and, well, before I stop, I just want to write on the other side, since I'm going to use the entire board. And so let's write here. So what we did was we took the curl of the electric field. So from this equation, so this is the curl of the electric field. So if I take the curl of this, I have to take the curl of that. So what I'm going to have is going to be minus d by dt curl of B. Okay? So we know from the other Maxwell's equation over here, the curl of B is equals to minus 1 over c squared dE by dt equals to mu naught times the current density. But we are interested in the wave, electromagnetic wave equation in a vacuum. Okay? So if it's a vacuum, then the charge density is 0 and the current density is 0. So for the curl of B, then I would have 1 over c squared dE by dt. All right. So now, if I substitute curl of B, which is 1 over c squared dE by dt, in here, okay, here, if we substitute that, would have the curl of E equals to minus d by dt. Instead of curl of B, I use what I have over here, this one. Okay, so that's, I hope you can see it. So that's 1 over c squared. So 1 over c squared dE by dt. Okay, so that is going to be minus 1 over c squared d squared E by dt squared. Okay. All right. So we use some identity, which I'm going to refer you to the note here. So let me go here. Okay. So I hope you can see this relation curl of A equals to the gradient of the divergence of A minus the Laplacian of A. So if I apply that in here, then I can write this one. I can rewrite this as the gradient of the divergence of the electric field. Okay, our vector in the electric field, and minus the Laplacian of the electric field. Okay, so that's what we get. Now let me refer you back to the Maxwell's equation here. Okay, well, this thing sometimes it forgets tracking me, so all right, so here, you know, if it is a free space, if it's a vacuum, since we don't have any charge in the medium, the divergence of E is 0. So if I apply that here, so this part is going to be 0, and since this is going to be 0, so what you would end up with is going to be the Laplacian of the electric field is equals to 1 over c squared d squared E by dt squared. So this is, if you recall, when we talked about wave on a string, which we derived the equation beginning from Newton's second law. So wave on the string, wave on a string. So we saw that it's given by d squared f by dt squared times 1 over v squared, okay, is equals to d squared f by dx squared. So that's for a one-dimensional wave that we determined last time. So comparing this one to that, you can see that this is a three-dimensional wave equation for an electromagnetic wave. So following a similar procedure, we can show that for the magnetic field, we find the Laplacian of the magnetic field B is equals to 1 over c squared dB by dt squared. All right, so I'm gonna stop here, and so I'm gonna upload this. I'm gonna upload this either on my website or on D2L, and I want you to let me know by email if you can easily follow me what I write on the board, and also you can easily see what I display on the TV screen here. Okay, so please let me know that before the end of Friday, so that I would be able to incorporate your feedback when I prepare the formal lecture, the lecture video that I'm gonna upload by either the weekend or maybe Monday. Okay, thank you. Bye.